Copper metal reacts spontaneously with a solution of silver nitrate. A coating of silver metal forms on the copper, while copper 2+ ions, which are blue in water, are released into the solution.
This is an example of what's called a direct redox reaction. Direct redox reactions are great when you want to have the oxidized species and the reduced species in contact with each other. You usually have really high percent yields, and it's usually fairly easy to separate out the products, which is cool. So in this reaction, they're taking copper metal, which is copper solid. They're adding 2 silver plus ions to it per copper. That's the silver plus aqueous. And they're ending up making copper 2 plus aqueous and 2 silvers. So if you look at that video at the end there's 2 things that are really interesting. First of all, there's that kind of mossy stuff over the copper. That's the silver. Silver in an unpurified form does not look like silver of a necklace. All right, it looks kind of like moss. All right. And anyway, that's the pure silver being made. Also notice though that there's a blue color. The blue color is indicative of the copper 2 plus ion being created. So these are just great examples of how you can use oxidized and reduced species to make things happen. And if you wanted the silver metal, you could essentially scrape it off the remaining copper and then collect it, purify it, and stuff like that. And you know the reaction was occurring because of the blue color of copper 2 plus. But also notice that the reaction happened right on the copper metal center. All right, that piece of wire, the copper wire that wound around, that's where the reaction took place. Direct redox reactions occur right at the place of where something's being oxidized or something's being reduced. So we won't get useful current out of this. We'll talk about current in a little bit, but you do have really high yields. You'd get pretty high yields of silver metal out of this one as an example. This picture shows it in more detail. On the left-hand side, you've got the copper wire in the beaker without any silver plus. And then in the middle, they've added the silver nitrate. AgNO3 is a pretty common reactant to add in these kind of situations. And what happens is the silver comes in contact with the copper metal. So the copper ends up giving up electrons to the silver. The silver becomes a solid silver metal, and the copper 2 plus ions go in solution. So on the far right-hand side, you can see there's a lot of the white atoms. Those are the silver atoms now that are connected to the rest of the copper metal. On the other hand, there's a lot of the kind of goldish looking ions floating in solution. Those are the copper 2 plus ions that have given up their electrons. They're floating around in solution, and that's what gives it its blue color. You can also, though, have what's called an indirect redox reaction, and that's what we're going to talk about a lot in this section. So in an indirect redox reaction, it allows the scientists to have some control over when electrons start flowing and when they don't. And what you basically have to do in a nutshell is you've got something that gives up electrons, the oxidized part, and you've got something that accepts the electrons, the reduced part. But what you do is you separate those 2 parts with a wire. So it's like you have 2 different compartments, if you will, and the wire kind of separates them. So when you connect the wires, then the electrons start flowing. And you can see in that little animation lower left, when the wire's connected, the little light bulb comes on. So this is an example of an indirect redox reaction. A chemist has control over when electrons flow, and this is the idea behind batteries. So for example, if you're flipping channels on the TV, you don't want the remote control to be on all the time. You just want to make things happen when you press the button. Well, pressing the button completes the circuit, electrons start flowing, and that's what allows you to change the channel, turn the volume up or down or something like that. So an indirect redox reaction provides a whole nother level of power, if you will, to what a chemist can do with a redox reaction. And again, you have to set up some kind of a wire system to make this happen, and we'll talk about the particulars here in a little bit. If you look in the animation, there's a negative and a positive. And remembering that electrons are negative, they want to run away from the negative side and run to the positive side. Opposites attract and same charges repel. So the electrons will go from the negative to the positive. And I encourage you to look, if you have one, a AA or a AAA battery, maybe at home, and you should see little positive and negative terminals on them. And now you know that electrons are coming from the negative side, and they want to move to the positive side, but they'll only do that when the circuit is complete. So when you put a battery in your remote control, nothing happens until you push one of the buttons for turning the volume up or something. That starts the circuit and gets the electrons going. Pretty cool. So these electrochemistry reactions are very powerful. Batteries by alone is just a fantastic process. We use batteries for like everything these days, and batteries are essentially the control of a chemical reaction where you have something being oxidized and something being reduced. Corrosion is another good use of these redox reactions, especially like in the Navy and in merchant marine ships. The seawater is really corrosive, and they need some way to fight that, or else their hulls would start rusting all the time. So they can find an appropriate metal to like kind of take away the corrosion first. It's a big time part. But even if you have just a car, the car gets rusty, especially if you're near the ocean after a while. You can then use these techniques then to fight the corrosion and keep your car in better shape. A lot of the chemicals that we use at Mount Hood come from electrochemical processes, and a lot of the soft drink containers that have aluminum for like cans, all of that aluminum had to be made through redox reactions. Aluminum metal is not found in the wild. You only have aluminum 3+. However, if you take that aluminum 3+ and add electrons to it, you can make aluminum, and that's going to make all the aluminum we have in cars and we have in cans and all kinds of other uses for it. But it's more than just aluminum. Sodium hydroxide and fluorine and lots of the different chemicals we use come this way. But probably more important, I guess, than anything is that it's used in our bodies. And you've probably been breathing right now. If you haven't, start breathing, okay? But anyway, breathing is actually a type of a redox reaction. In our bodies, we have the heme group, which is an iron center kind of, and it takes an oxygen from the air and binds it. And then the heme goes through our bodies, and the oxygen is released later on in a place that needs it. This is a type of a redox reaction. It's a biological redox reaction, and these are also really important. So we need to talk about these and see what kind of control we can have, and also figure out how we could set one up if we wanted to. An electrochemical cell is basically a fancy type of chemical system where you have something being oxidized and something being reduced. But instead of putting them in contact with each other, we somehow have a way to control the reaction. It is usually through a wire, all right? So an electrochemical cell is just a fancy way to have at least the possibility of control over your chemical reaction. Now, believe it or not, there are two types of electrochemical cells that are possible. And the one we're going to talk about the most is called either voltaic or galvanic. And those are just product-favored electrochemical cells. So you put them together, you put them in your remote control, and they work, all right? If you're going to have a product-favored reaction, that's going to create electrons. Voltaic and galvanic cells are product-favored. They are batteries that work, and that's what we're going to talk about a lot in this section. However, you can have a reactant-favored reaction. So you put your chemicals together and nothing happens. Those are called electrolytic cells. They need what's called electrolysis to make any chemical change happens. We'll talk about this towards the end of this chapter, but those won't happen unless you apply electric current. And they do have utility, which is absolutely crazy. So voltaic and galvanic is just an electrochemical cell that works as is, but if you have a reactant-favored reaction, then you need to have electricity go through it. It's called an electrolytic cell.